Hello everyone, welcome to biotechnotebook. In this video we are going to see how to calculate residence time distribution. Okay, so in the last video already we have seen about what is ideal flow, what is non-ideal flow, and what is residence time and residence time distribution. Everything we have studied in the last video. Okay, in this video we are going to see how to calculate this residence time distribution. Okay, so before starting this video, just I'll revise what is residence time and what is residence time distribution. So let's see what is residence time. Residence time is the time it takes a molecule to pass through a reactor is called the residence time of a molecule in the vessel. Okay, that means how much time a molecule is spending inside the reactor is known as residence time. Okay, only ideal batch reactor and ideal plug flow reactor, the molecules spinning inside the reactor is same. For all other real reactors, the molecules won't have same residence time inside the reactor. So for non-ideal reactors and real reactors, we have to calculate residence time distribution. In non-ideal reactors, the elements of fluid taking different routes or pass through the reactor. So it may take different lengths of time to pass through it. So there is a distribution of residence time of the fluid material within the reactor. There are many reasons for spending your molecule different time inside the reactor. It may be due to bypassing or short circuiting of the fluid, channeling of the fluid, turbulent mixing and diffusion, and due to stagnant region formation. Okay, let's see how to calculate this residence time distribution. Residence time distribution is calculated as exit age distribution. That means the distribution of the residence time for the stream of fluid leaving the vessel is called exit age distribution, or the residence time distribution RTD of fluid. Okay, so you are going to measure residence time for the stream of fluid leaving the vessel. So this is known as exit age distribution. So here E has a units of time inverse. Then this RTD is determined experimentally by using an inert called as tracer. So inert means non-reactive chemical. So tracer is used to measure the residence time distribution. Tracer is nothing but it is an inert, that is non-reactive chemical. Okay, so let's see the characteristics of tracer. It should be non-reactive, that is an inert chemical. Then it should be completely soluble in the system of fluid. Okay, so it should be completely soluble with your feed stream. Then it should be easily deductible. Then only we can measure the concentration of tracer in the effluent stream. Then it should have physical properties similar to those of the system. Okay, that is, it should have the similar physical property to those of your feed. Then it should not absorb on the walls or other surfaces in the vessels. Okay, then colored materials such as dyes and radioactive materials are commonly used as a tracer. Okay, so your tracer are nothing but dyes or radioactive materials. This tracer is in the form of its concentrated solution. Then RTD is determined experimentally by injecting your tracer into the reactor with your feed stream. Okay, then we are going to measure the concentration of your stream at the effluent as a function of time. So we have to inject the tracer into the reactor. So there are so many methods are there to inject your tracer into the reactor, but the most common method used for injecting the tracer are pulse input method and step input method. Okay, in this video we are going to see about pulse input experiment. In the next video we will see about step input experiment. Okay, in pulse input method you will inject your tracer in one shot, okay, as soon as possible. Okay, in very short period of time you will inject your tracer in one shot. Okay, that is pulse input method. Then you will find out the concentration of your tracer in the effluent stream. Okay, this is pulse input method. In step input method you will inject your tracer concentration at a maximum level. Then you will continuously inject your tracer. Then continuously you will measure the concentration of your tracer in the effluent stream. In pulse input experiment, a known quantity of tracer, just consider m kg or moles of tracer, is injected in one shot instantaneously. That is, in a very short period of time you have to inject your tracer in one shot with the feed entering into the reactor. Then you have to record the concentration of your tracer in the effluent stream. This is your pulse injection curve. So this is concentration of your tracer with respect to time at the inlet of your vessel, and this is your pulse response curve. So the concentration of your tracer with respect to time you recorded at the outlet of your vessel. Okay, and this pulse response curve is known as C pulse curve. Okay, next let's derive the expression for E and T bar. T bar is nothing but mean residence time. Okay, so the amount of tracer material del M, that is del M means very small quantity of tracer leaving the vessel between time T and T plus del T. So in a very short period, the amount of tracer leaving the vessel is obtained by writing a material balance for the tracer. Okay, let's see the material balance of tracer. So for before that, let M naught is amount of tracer we suddenly injected at time t is equal to 0 in the inlet of your reactor in in a very short time span. Okay, then del M is the amount of tracer exit from the reactor in time between T and T plus del T. Mu is the volumetric flow rate of the effluent stream from the vessel. General material balance for any chemical reactant is input, that is the feed entering into the reactor, is equal to output, that is the product leaving the reactor, plus disappearance by reaction. Okay, the rate of the reaction plus accumulation. Chemical deposited inside the reactor is known as accumulation. Okay, so now just let's see for material balance of tracer. Input, that is the amount of tracer entering inside the reactor in moles per time. Okay, here your input is in moles per time, and output, that is the amount of tracer leaving the reactor in moles per time. Disappearance by reaction. So tracer won't involve in any reaction, it is an inert chemical, so there is no reaction takes place inside the reactor. With this term turns to 0. Okay, then accumulation. So in the characteristics we have seen that tracer should not be deposited on the surface or any walls of the reactor. So this term, accumulation term, also turns to 0. So you will get only input is equal to output. Okay, so input in moles per second, Lm, that is amount of tracer injected into the vessel with respect to time, is your input. So input is del M divided by del T is equal to output. So output is nothing but your concentration of your tracer at the volumetric flow rate. So if you see the unit of these two terms, that is unit of concentration is defined as mole by volume. So moles of tracer divided by volume, and unit of volumetric flow rate is volume divided by second. So if you cancel these volume, you will get in the unit of mole per second. Okay, so in both the side you have same unit, mole per second. So now rearrange this equation, you will get del M is equal to C nu del T. Okay. So this is your equation number 1. Then just divide equation 1 by M. So you will get del M divided by M is equal to C nu divided by M into del T. You can write this as C divided by M divided by nu into del T. Okay. Here M is total amount of tracer injected into the vessel, and del M divided by M is fraction of material that has residence time between time T and T plus del T. Then let's define E as C nu divided by M, or you can write it as C divided by M by nu. Then just substitute equation 3 in equation 2. So in equation 2, del M divided by M is equal to C nu divided by M. So E is equal to nothing but C nu divided by M. So del M divided by M is equal to C nu divided by M is E. So E into del T. Okay, so you will get this equation as del M divided by M is equal to E into del T. Then whenever M is not known directly, it can be obtained by measuring the tracer concentration in effluent stream, and you can sum up all the amount of materials and del M between T is equal to 0 to T is equal to infinity. So for this we have to write equation 1 in differential equation. So equation 1 is del M is equal to C nu del T. So in differential form you can write it as dm is equal to C nu dt. Okay, so dm is equal to C nu dt. So now you can integrate this equation as 0 to m dm is equal to 0 to infinite times C nu dt. Okay, so here nu is constant, so you can take it outside. So integration of 0 to m dm is equal to nu integration of 0 to infinity C dt. Okay, so if you integrate dm, you will get m So limits is 0 to m. So m minus 0 is equal to m is equal to nu into integration of 0 to infinity c dt. Okay. So m divided by mu. M divided by mu is equal to integration of 0 to infinity c dt. So combining equation 3 and 6. So your equation number 3 is E is equal to C divided by M by nu. So now you can substitute this equation 6 in this equation number 3. So you will get E is equal to C divided by M by nu. So M by nu is nothing but integration of 0 to infinity C dt. So here integration of 0 to infinity c dt is area under your C curve. So C curve is nothing but graph obtained between time and tracer concentration at the outlet. So you can numerically calculate it as 0 to infinity c dt is equal to Ci into del Ti. You can obtain E value from the tracer concentration, time, data, then E curve from the C curve. So C curve is nothing but your graph plotted between time and concentration of your tracer. Your area under the curve is m divided by nu. Then E curve is obtained by plotting the curve between time and E. So E can be obtained from the tracer concentration and time data. There is a restriction on the E curve, that is the fluid only enters and only leaves the vessel one time. Okay, it means that there should not be any overflow or diffusion or upflow eddies at the entrance or at the vessel exit. This condition is closed vessel boundary condition. So for the condition for E curve is there should be a closed vessel boundary condition. Your fluid should flow only one time inside the reactor. In open vessel boundary condition means elements of fluid can cross the vessel boundary more than one time. Okay, that condition is known as open vessel boundary condition. So this is your E curve, that is exit age distribution curve E. So this curve is plotted against time versus E value, and if you calculate area under the curve is equal to 1, that means fraction of all the material that has resided for a time t in the vessel, this between time t is equal to 0 and t is equal to infinity is 1. Okay, that is sum of fraction of all the materials inside the reactor is equal to 1. So you can represent RTD in such a way that area under the curve is unity, or you can represent it as integration of 0 to infinity E dt is equal to 1. Then this procedure is called normalizing the distribution. From this graph you can denote the fraction of younger than age t1, that is younger than age t1 less than time t1 as integration of 0 to t1. So integration of 0 to t1 E dt. Then the fraction of material older than t1. So after this time t1 is, you can denote as t1 to infinity. So t1 to infinity E dt. So if you calculate area under the curve 0 to t1, you will get the value of fraction younger than age t1. Okay. If you calculate area under the curve from t1 to infinity, you will get the value for integration of t1 to infinity E dt. The total area under the curve, that is 0 to infinity E dt is equal to 1. Okay. If you sum up these two, you will get the value of 1. So you can write it as 0 to infinity E dt is equal to 1 can be represented as integration of 0 to t1 E dt plus integration of t1 to infinity E dt, that is equal to 1. Okay. So from this equation you can calculate younger age than t1 and also older age than t1. Okay. So older age than t1, that is integration of t1 to infinity E dt is calculated by 1 minus integration of 0 to t1 E dt. Okay. So if you want to calculate younger age that less than t1, 0 to integration of t1 E dt, you can write it as 1 minus integration of t1 to infinity E dt. Next, mean residence time. We can calculate mean residence time for the tracer. So the formula to calculate mean residence time is integration of 0 to infinity t into c dt divided by integration of 0 to infinity c dt. Okay. Numerically, you can write it as summation of ti ci del ti divided by summation of I ci del ti. T bar is equal to V by nu, that is V is volume of the vessel and nu is volumetric flow rate. T bar is mean residence time. We have another RTD function E naught. It is a dimensionless function. Here E naught is defined as T bar into E. Then we can define the parameter theta as T divided by T bar. Okay, E theta is equal to T bar into E. Formula for T bar is V divided by nu, and E is equal to C divided by M by nu. So this nu will cancel it out. So you will get V divided by M into C. So E theta is plotted as a function of theta. So theta versus E theta, you will get the curve like this. Then here theta is nothing but it represents the number of vessel volumes of fluid that have flowed through the vessel in time t. This is all about pulse input experiment. In the next video we will see about step input experiment. Thank you for watching my videos.